Welcome to the third lecture in Unit 2, Sculpturing the Earth's Surface. This is the third lecture discussing the concept or the field of geomorphology, that is the shape of the Earth. Typically what geologists mean is the shape of the Earth's surface when they talk about geomorphology. This chapter will deal with the third important set of forces that impact and shape and control the form and structure of the Earth's surface, that is glaciers, deserts, and wind. It's a catch-all. In the first two chapters, we looked at weathering, soil mass wasting, and in the third or the second lecture in this unit, we discussed running water and groundwater. Pardon the motorcycle sound if you heard that. I'm doing this from my home office, and sometimes there's some outdoor or indoor noise. Anyway, Unit 2, Sculpturing the Earth's Surface, Chapter 6, Glaciers, Deserts, and Wind. Glaciers are part of two basic cycles in the Earth system. And what I mean by that is that glaciers are both part of the hydrologic cycle and the rock cycle. They form and grow and are reduced in size due to changes and variations in the water cycle, or how water moves in global pathways. Stepping back for 1 second, glaciers are a general catch-all term for frozen water collected on the surface of the Earth. So large ice sheets or big snowfields. But fundamentally, they're collections or accumulations of frozen water or solid water. Glaciers are both part of the hydrologic cycle. That is, they grow and shrink due to changes in how water moves or throughout the globe. And they are also part of the rock cycle in that they can impact tectonics, or are impacted and can impact tectonics. That is, they can create large masses of weight on the Earth's surface and cause flexures or distortions in the Earth's crust. They also are able to transport a lot of material throughout the areas in which they exist, and in fact can mobilize material or are erosional and transportation agents for geological material or solid material, even further than their aerial extent. That is, for example, icebergs or ice rafting can transport northern latitude or high latitude sediment from areas that are eroded by ice sheets. They can transport them into the ocean, and then the ocean then can transport them around the globe. So a glacier is a thick mass of ice that forms over land from the compaction and recrystallization of snow, and it shows evidence of past or present flow. So the important part of that definition is that it's let's get this back. The thick mass of ice forms over land from compaction and recrystallization. An important word in there is actually accumulation. So let's type that in. Accumulation. Compaction and recrystallization of snow. And it shows evidence of past or present flow. There are various types of glaciers in the Earth system. Valley or alpine glaciers, they're usually small in aerial extent, and they form in mountainous areas. So that's what you see. By the way, glaciers are year-round features. So this isn't a ski mountain in West Virginia that has snow in the winter and is verdant and green and has no snow in the summer. Alpine glaciers by definition, or glaciers by definition, have year-round snow, and they are actively accumulating in certain areas. So valley or alpine glaciers are typically smaller, high altitude, and typically form in the mid latitudes or the northern latitudes, but there are some tropical and subtropical alpine glaciers. That is, in the high altitudes of tropical regions, especially in South America, you can get glaciers. The other main type of glacier is considered or called an ice sheet or continental glacier. These are large in aerial extent, very thick. Typically, I think that they are 50,000 kilometers or greater in area. That's the cutoff between ice sheets and what are called ice caps, smaller, large-scale continental accumulations of ice and snow. The current ones that exist in the U.S. or sorry in the globe presently are over Greenland, which is a reasonably small in comparison to the Antarctic ice sheet. It's interesting. The ice sheets contain a lot of water. This is not thought to be a likely scenario, but it certainly is in the realm of possibility amongst global climate change scientists. But the Greenland ice sheet, if it were to totally melt, it would cause sea level to rise by about 6 meters. That's how much water volume is in the Greenland ice sheet. That's in contrast to the Antarctic ice sheet, the East Antarctic ice sheet and the West Antarctic ice sheet. The East Antarctic ice sheet is huge. The West Antarctic ice sheet, if it were to melt, would also contribute about 6 meters or 5 meters of sea level rise around the globe. Now, that sea level rise would be distributed unequally due to gravitational forces and ocean circulation, but in general, about 5 meters, which is a little bit more than 15 feet, 15, 16 feet. Now, the East Antarctic ice sheet is absolutely ginormous. If it were to melt, now much of it is below sea level, but due to crustal flexure and structural changes that it has induced on that continent. But if it were to melt, the amount of ice that it contains would cause sea level to rise by 45 to 50 meters. That's right, 45 to 50 meters. That's a lot. Ice caps and Piedmont glaciers are much smaller features. Ice caps are less than 50,000 square kilometers, and Piedmont glaciers are smaller features in mountainous or they're not necessarily alpine, but they're higher altitude than typical ice sheets. This is just a graphical representation of the ice sheets, the major ice sheets that exist today. Greenland in the northern latitudes. Canada is here. Europe is around here. This is Greenland. If you can look on a globe and find Greenland, but it's a continental ice sheet. Now, the ice that covers the North Pole or that covers the Arctic Ocean does not actually contribute to sea level rise because it's already in buoyancy or equilibrium with the water that's surrounding. Because it's not a continental glacier, it doesn't represent any sea level rise. If it were to melt, it would represent a change in transportation routes for human beings, that's for sure. And in this Antarctic ice sheet, you've got the East Antarctic ice sheet here, and the West Antarctic ice sheet up here, and the East Antarctic ice sheet down here. It's a really relatively gigantic ice sheet compared to the West ice sheet and the Greenland ice sheet. Glaciers move. That's part of their defining characteristic. There are different types of glacial movement, and they're often somewhat analogous to the way rock can actually move. You can have plastic flow that is more like fluid flow. It's deformative flow, or ice can actually move over. It moves very, very slowly, but it can move generally with liquid properties or as a liquid. It just kind of flows, usually down gradient, in fact always down gradient by gravity. The other types of glacial movement can be slipping. So oftentimes in the interface between an ice sheet and the underlying bedrock, there's a lot of friction. There's oftentimes liquid water, and you can or glaciers can move in much more abrupt and discrete motions. That is, they can slip periodically along that bottom surface. So the upper regions or the middle regions of glaciers typically are the plastic flow regime, and the lower regions near the bedrock interface are more characterized by slip movement. On the uppermost 50 meters, generally, again, that cutoff is not a rigid cutoff. Generally speaking, in the upper 50 to 70 to 30 meters of an ice sheet, there is much more fracture in the glacial surface. And that's due to the fact that there's less consolidation. The ice sheets or ice and snow that is accumulating is had less time to really compact and form a cohesive mass. And that movement down below, the plastic flow and the slippage, will cause perturbations in the surface and generate brittle fracture and crevasses. From a large aerial perspective, there are two major zones, or one can view glaciers as having two significant zones, and that has to do with what is actively happening. Usually there's a zone of accumulation where the glacier is forming and accumulating. That is the area where snow is falling, ice is falling, where climate is such that melting is much less, or annual melting, that is summertime melting, is less than wintertime accumulation. That is where a glacier is actively growing, getting larger, building up material. And then there's the zone of wastage, and that is due to either melting or mass wasting. You can actually lose glacial material when it interfaces the sea as icebergs form and move off into the sea. And that is usually where either climatologically there is more summertime melting than wintertime accumulation, or the flow is such that, or the rate of flow is such that ice is being lost outside the system. This shows the generalized delineation of those two areas. Up here in the upper regions, up in the either higher altitude or higher latitude areas where it's colder, where summertime melting is less than wintertime accumulation, more snow falls each year than melts in the summer. And this is where the glacier is building, actively getting thicker as it builds up. Flow, you see, is generally, or is always, downhill, gravitationally driven. And eventually you get to that point where summertime melt exceeds wintertime accumulation. And that line, or that area, or that region, is the delineation or the boundary between the zone of accumulation and the zone of wastage. All the snow from the previous winter melts along with some glacial ice. So anything that is actively accumulating here in the winter, like active snowfall on the surface, won't last through the summer in the zone of wastage. And as more material moves down slope, even some of that material that has accumulated up here in decades or millennium past will eventually get here and start to melt and or be wasted off into the ocean or whatever that boundary is. You'll notice I said in years, decades, or millennium, glaciers do move very, very, very slow and can accumulate over millions or thousands to hundreds of thousands to sometimes millions of years. Glaciers are active agents of erosion. In two main modes. They pluck. They can lift blocks of rock, whether they're huge boulders that are 15, 20, 30, 40 feet across, or they can do a much finer scale, but very significant in terms of the volume or mass of rock that's eroded, erode by abrasion. Especially when you consider glaciers will be carrying lots of material, lots of geologic material in their lower zones because they're such strong agents of erosion and transport. You're basically, the bottoms are essentially like sandpaper. The rocks that are entrained in the lower regions of glaciers that are moving will cause further abrasion and further erosion, and you can get very, very, very fine material generated by glacial erosion. And in fact, bedrock that is had glacial movement above it often has grooves and lines that are scoured in the surface in the direction of the glacial movement. In fact, you can find that in many places in the upper Midwest and upper East, Middle Atlantic and Northeast of the United States from the last glacial. You can find plenty of examples of rocks, bedrocks remaining that you can slide your fingers along and you'll feel the direction of glacial movement due to the gouges that are in the rock. They're quite strong. Also, you'll find something called glacial erratics periodically around the upper Midwest and Northeast. These are huge boulders of rock. It can be anywhere from, a meter across to 30, 40, 50 meters across. That's not an exaggeration. Transported from hundreds of miles away by glaciers. There's no rock like these boulders in the near vicinity, but they are exactly like rocks that are from hundreds of miles away to the north. Glaciers have tremendous power to move earth material and shape the surface of the earth. Lots of different landforms are created by glaciation or glacial erosion. This is a list of typical alpine glacier features: a glacial trough, hanging valleys, cirques, arêtes, horns, and fjords. Next, we'll look at a graphical representation of those. This is a cartoon or a schematic of the different types of alpine glacier features. A glacial trough, you'll notice, is a very U-shaped valley in profile. That's typical for glaciation. River erosion is typically V-shaped. We discussed that in running water unit of chapter 5. Downcutting by streams is typically occurs in a V shape until you get down to that lower zone of the profile where meandering and floodplains take place. But glaciers, when you find high altitude mountainous U-valleys, U-shaped valleys, those are most always caused by glaciation. Large glaciers traveling through this valley, eroding away the material as it goes. Higher up in mountainous or alpine regions, you have arêtes, which are it's a French term, but it's basically a large or long knife ridge between two hanging or U-shaped valleys. We have a U-shaped valley over here and a U-shaped valley over here, and this arête is the divider between the two. A cirque is usually found higher up in alpine regions. It's the beginning or a hanging U-shaped valley. It's the start of a glacial, usually it's always in the zone of accumulation, and that is the start of a U-shaped valley that will move down in. Cirques can also accumulate water, and a tarn is basically a glacial lake or a place of accumulated and steady surface water in a former cirque. Horns are very, very recognizable. They are these kind of very sharp, pointy, mountainous zones, usually very, very high altitude, and those are a product, again, of alpine glacier formation and cirques. They're the kind of the boundary, the arêtes between multiple cirques. Paternoster lakes are similar to tarns, but they are basically steps down during or within hanging valleys. Hanging valleys are these U-shaped glacial valleys that end up kind of at a cutoff or with a large drop, and that's due to larger glacial movement through a U-shaped valley and a hanging valley or another mountain glacier coming down in and joining a tributary, as it were. So a horn is like I said, very, very archetypal thing, and the Matterhorn is the prime example of what a glaciated interior and alpine regime would look like. Now, glaciers are not only agents of erosion, but they're also agents of deposition. They are sediments that are deposited through glacial transport are very, very characteristic, often very recognizable. They typically, glacial sedimentation, there's a main type is called glacial drift, and can be divided into two subforms. That's till and stratified drifts, stratified drift. Till is material that's deposited directly by ice. So as solid material is carried along the bottom of a glacier, and eventually, if that glacier gets to that zone of wastage where it's no longer actively accumulating and starts to dissipate, that material is no longer able to be carried and it's dropped. So material that's directed or deposited directly by ice is called till, but when at that edge of that zone of wastage where the glacier is no longer moving, you're also going to have a lot of water coming out of the bottom of the glacier and off of the top, which has the ability to transport material as well. When that water carries material or load, bed load, suspended load, and dissolved load, when it eventually drops its material, that is considered stratified drift. And the reason it's called stratified drift is because it's going to be sorted by grain size. It's stratified. Till is often poorly sorted, unsorted, because it's just a big old jumble of material, both really, really fine glacial flour and larger cobbles and boulders and other things that are huge. Glacial till is unstratified and unsorted. That is, unstratified meaning it doesn't have very many, it doesn't have recognizable layers. Um, there's no real layering, and just a mess of a mix of large boulders in here and smaller clays and silts and muds. A cobble, that's a generalized grain-sized term. These are cobbles in there. They're very large. They can be fist-sized to size of a pineapple type of thing. Depositional features of glacial deposits of till fall into several different types or forms, but the word moraine describes them all. They are layers or ridges of till and can often be used to map the extent and movement and progression of glacial systems. There are different kinds of moraines. One of the most famous lateral terminal moraines is the region of Long Island, New York. That is entirely a moraine. If you look at a map of the U.S., you'll see this long lateral line off the coast of New York, and that is the edge of a glacier. Other depositional features are outwash plains, kettles, drumlins, eskers, and kames. Here we have a image of a few of those different types. Moraines are basically large ridges that can form in various different directions based on the glacier's movement. If we have a glacier that was moving in from left to right and then started to retreat, you can imagine when that glacial surface was right here and it started to retreat, it left a bunch of material, and that is that it had pushed up. It's almost like a bulldozer. It pushed up this large layer of material, and then when it retreated back, it left this ridge. That's the same thing, or as is happening here at this lateral moraine. So these two moraines are features that are basically bulldozed layers of surface sediment that have been left by glaciation. What's left in the after a glacier retreats from different areas, you have eskers, which are features that are caused by water or flowing water deposition coming out from the bottom. Kettle lakes are left by are depressions in the ground that can accumulate water that are left by large either boulders or just the weight of that glacier on that area that caused a depression. Drumlins are are a type of lateral moraine that is caused by dragging material, and this is a picture up here of an actual drumlin. It's a really interesting shape. Ice drags material and leaves it in that characteristic pattern. Kames are areas of scoured and eroded bedrock that are represented or that remain on the surface. And eskers are outwash features. Glaciers have been occurring throughout all of Earth's history. This graphic is, we'll change this, the last glacial ice age. This slide is basic description of the last glacial, which began 2 to 3 million years ago. But glaciations, ice sheets, have been occurring on the Earth's surface as far back, at least as geologists know, as far back as 2 to 3 billion years ago in the Proterozoic and the Huronian glaciation. This last division of geologic time where the last glacial occurred, or the last major global ice sheet. And when I say global ice sheet, I don't mean it covered the entire Earth. But it was a significant ice sheet that reached down to maybe 40, 35 degrees northern latitude. This division of geologic time is called the Pleistocene epoch, and ice covered almost 30% of the Earth. It was a pretty big glaciation. Here's a map of what is thought to be the lower extent of that glaciation. Here we've got Long Island is right in there, and so you can see that where that glacial moraine or that terminal moraine would be. But we've got some significant intrusions of ice down into the middle of the Midwest. Also over much of the North American or Canadian shield, over Greenland and much of Northern Europe. Indirect effects of ice ages are that it can cause the climatological effects, and the climatological forcings can impact the distribution and extent of different organisms of the biological or of the biosphere. Animals and plants which are climatologically influenced, can migrate or will migrate based on glaciations. Although remember, glaciations occur over very, very slowly, over thousands to tens of thousands to hundreds of thousands of years. So we're not talking about a family of antelope picking up and moving 500 miles because all of a sudden the ice appears next door. We're talking about large kind of generational, very long-term changes in the distribution of different ecosystems. Other effects are rebounding upward or deformation downward of Earth's crust based on the hydrologic cycle are controlled by the extent of ice sheets. And so you have feedback cycles that will complicate and make the global pathways or global circulation pathways, which ultimately control weather, alter. The causes of glaciation are numerous, and again, we're getting into the system science of it. Feedbacks are quite important, both negative and positive feedbacks. But a successful theory for accounting for or to explain glaciation must account for the cooling of the Earth as well as short-term climatic changes that occur both before, during, and after ice ages. Geologists interpret past ice age events looking at using the rock record. Remember, all rocks tell a story, and both the chemistry and distribution of rocks around the globe can be used to read the story or read the clues about what caused and what the effects of glaciations have been. Proposed possible causes for ice ages or large, globally significant glaciations are plate tectonics, that is, continents move over long periods of time. Glacial or continental arrangement can influence oceanic circulation, can impact atmospheric circulation, can impact the water cycle or the hydrologic cycle quite dramatically, and can therefore affect and control atmospheric chemistry, which is ultimately one of the most important factors in terms of global climate, particularly the amount of carbon dioxide in the atmosphere. There's also things that are not directly related to Earth processes, but are related to astronomical processes or astronomical factors. Something called the Milankovitch hypothesis, which is that changes in the shape and the mode of Earth's orbit around the sun can actually cause variations and changes in the amount of solar energy or heat energy that the Earth absorbs over long periods of time, 20,000, 40,000, 100,000 year cycles of obliquity, precession, and eccentricity will impact the amount of heat that's on the Earth's surface, and therefore the climate and how likely it is for snow to accumulate and to remain through the summer, or for snow to melt. And after all, essentially the accumulation of solid water on the continents is what ultimately drives ice sheets. Changes in climate over the past several 100,000 years and back in through to the millions of years in cycles are closely associated with variations in the Earth's orbit. That is, physicists and astronomers know how the Earth's orbit will, the orbit around the sun will change, the wobble of the Earth's axis, as well as the kind of the tilt of the Earth will change. Those physicists know those very, very well, and it just so happens that Earth glacial cycles in time pretty much match those three things, in addition to some other things, but those are very, very important factors. Moving on to deserts, the second in our second aspect of our discussion of Chapter 6. Deserts are globally significant. They weathering occurs. They're a source of sediment and fine material into the atmosphere, which can have far-reaching effects. Wind-blown dust from arid climates can actually impact tropical biology in the oceans hundreds of and thousands of kilometers away. So deserts don't only have impact for the people that live near or in them, they are globally significant features. Weathering in deserts is not as intense as it is in tropical regions, and that's because weathering oftentimes requires water. However, weathering does occur in desert regions. It's mostly mechanical weathering. Some chemical weathering does occur. Thin soils can develop. Clays can arise. But for the most part, it's mechanical. Water is what people mostly think about, or lack of water, when they think about deserts. Streams do exist, but they're dry most of the time. Desert streams are typically ephemeral or intermittent. They only flow during rainfall, and around the world, different names are used for desert streams. Wash or Warsh in the American Southwest, Arroyo, Wadi, Donga, and Nula are terms used for ephemeral or intermittent, that is, streams that do not carry water year-round. Rain does occur in deserts, however, it is unable to infiltrate or is unable to infiltrate as much as it would in other areas where there's better soil development. When you have very, very thin soils and you go straight to bedrock, there's not a whole lot of space for that water to accumulate and to stay put. Instead, it sits on the surface, either runs off or evaporates very, very quickly. Most erosional work in the desert is done by running water. This is an image of a dry stream bed. You can still see features of water flow. You can see ripples down here. You can see channelization with these walls on the side. So it looks like a stream, but it just doesn't have water in it. So geologists can oftentimes, interpret landform features, or geomorphologists can see landform features. Even if there's no water running, you can see evidence of water, and you can interpret or make conclusions about the environment that you're in, or the paleo environment, that is the ancient environment that existed at that place in that time. This is that same place with water running through it, and you can exactly see where you would anticipate stream flow. Not much vegetation on the ground because you're probably having erosion, scouring, bed load moving through. But on the sides where there's water in the past, you do get some growth. Evolution of the desert landscape is often follows the same pattern. It's a pattern that is known to geologists, or it exhibits characteristics that is described by geomorphologists or earth shape scientists as the basin and range. Typically, uplifting of crust causes isolation of interior basins, that is, mountain ranges on all sides. And interior drainage or stream flow from those high altitude alpine regions produces things called alluvial fans. Remember, alluvium are deposits from stream flow. So you get alluvial fans and playas. Erosion of mountains that bound or that constrain these basins causes local relief to eventually diminish. So basically, these uplifted mountain ranges with basins in between will eventually, the mountains will get smaller as they erode, and the basins will kind of fill in and get higher. And so you get eventually these very, very flat areas with the few and far between bedrock knobs called inselbergs. So here we have a general schematic of what's happening, or what typically happens with an alpine desert or a mountainous desert. You have uplift of crustal blocks. These lines between these blocks in the crust show that the crust is being deformed by tectonic forces and lifting up masses, where you get these big ranges of mountains at the edges of these uplifted crustal blocks. But in between those crustal blocks, you have these valleys. Now, typically in any kind of high altitude area, you're going to get a decent amount of rainfall and stream flow, and flowing water causes erosion. And these high mountain ranges will start to erode and will start to deposit alluvial fans, that is, deposits of alluvium, stream eroded debris or stream transported material on the basin or the base of these mountains. Over time, as more and more the high mountain erodes and the alluvial fans build up, you actually get these alluvial fans that start to coalesce and become part of the single system, and that's a bahada. These playa lakes are no longer filled with water. They're typically dry or at least ephemeral, and your mountain ranges show much more erosion. They're much less sharp. They're more rounded, and over time, eventually they round all the way down into these inselbergs, these isolated pockets of bedrock protruding through the surface with large areas, flat expanses of essentially eroded mountain material or alluvium that is coalesced from long-term, thousands to hundreds of thousands of years of erosion and deposition. Wind is a important factor in desert processes. Wind causes a lot of erosion. It also causes deposition. Wind is able to lift loose material from the desert floor and can produce blowouts, basically pockets in the desert floor, or also what's called desert pavement. That is really, really hard surfaces of larger material that is not able to be blown by wind. It also causes abrasion. That is, as the wind moves grains of material across the desert surface, those grains act as erosional agents, and the impacts of those grains on what's left on the ground can actually cause more mechanical weathering. Formation of desert pavement graphically looks like this, where you have a mixture in a desert of unsorted, fine material interspersed with larger grains, larger crusts. And as that wind moves across, it can only transport the fine material. Eventually, it gets to the point where so much fine material has been removed, all that remains are these larger cobbles and gravel and pebbles that wind is no longer moving anything, and you have a very, very hard, relatively impermeable surface on the desert floor. The other way in which desert pavement can form is when you have bedrock and mechanically weathered bedrock with large pebbles, gravel, boulders, and cobbles. Eventually, wind-blown material can accumulate in those cracks, in those surfaces, but due to gravity and general sorting processes that naturally occur, that fine material percolates down and kind of lifts the heavy material up. Or the larger material, I shouldn't say heavy, lifts the larger material up, and those fine grains are down below, and eventually you get a layer of relatively impermeable large grain material at the surface. Wind deposits can be characterized a couple different ways. Loess is a general catch-all term for deposits of wind-blown silt. They are often aerially quite extensive. They cover large areas, and primary sources are deserts and glacial stratified drift. Remember, glacial drift is oftentimes unsorted, but in a stratified drift deposit, there's going to be a lot of that glacial flour, which is very, very, very fine. Sand dunes are the other general zone of desert deposits. Sand dunes are mounds or ridges of sand formed from the bedload, that is movement of material along the land-air interface. It's not wind-blown. It's not entrained. It's not carried aloft by wind. It's bumped along the ground by wind. So it is still wind carried. It's just bedload. Characteristic features of dunes are a slip face, which is the leeward slope of the dune, that is the over past the ridge downstream of the wind direction, and crossbeds, which are sloping layers of sand in the dune. Crossbeds oftentimes will show up in rocks that are ancient, hundreds of thousands, millions of years old. They're basically dunes that have been lithified, turned into rock, and geologists can therefore interpret wind direction and wind intensity based on sandstones that exhibit dune features. The formation of sand dunes generally follows a path where you move small bits of sand. They accumulate. Remember, angle of repose, how steep a surface can be before it starts to collapse. It's a mass wasting event. Sand dunes will accumulate up to their angle of repose for the particular material that is being accumulated. And as they get bigger and bigger and bigger, they build up over each other. And you get these features that are called crossbeds. That is, the layers of buildup will cross over. And eventually, in geologic time, as those layers get compacted and lithified and buried deeper and deeper in the earth and turned into rock, those crossbeds or those layers can be preserved. somewhat in graphical representation here, but an actual representation up here. It's quite a beautiful cross-section of cross-bedded dunes. And so a geologist would interpret that this area was arid at one point, was impacted by wind, and one could even use the direction of these crossbeds to determine directions of wind and even magnitude. And directions of wind and even magnitude can be used to interpret climatological things, like where zones of high pressure, where zones of low pressure were in the globe at that point in time. Different types of wind deposits or different types of dunes, particularly, just like glacial features, have names: Barcan dunes, transverse, longitudinal, parabolic, and star dunes, and they all are representative or caused by slightly different types of movement of wind. Barcan, transverse, and Barcanoid dunes all represent generally single direction or unidirectional wind. Wind moving in this graphic from lower left to upper right will produce these generalized forms of Barcan transverse, which look very, very wave or ripple-like, or Barcanoid, that is kind of a combination of transverse and Barcan. Whereas variable wind directions will get, but coming from a generalized one side, will generate longitudinal dunes instead of transverse. Parabolic dunes are often near coastal regions and are kind of opposite of Barcan. And star dunes are where you have wind directions that are unpredictable or that are highly variable, and the dunes are a little bit more chaotic, similar to kind of dendritic drainage patterns. When you don't have any controlling, uniform direction, you tend to get chaotic systems. And that is the end of chapter 6. I hope the lecture was clear, and remember to review your text. You may feel free to review these lectures, but definitely review your text before taking the quiz for Unit 2, and I'll see you again in Unit 3, Chapter 7.